Failure, as a rule, starts at the weakest link. It sort of makes sense, but if you compare it with what happens with stiffness, then it's actually quite insightful to think about it. If you're trying to calculate stiffness where you use a multiple set of materials, you will calculate the corresponding stiffness of each material and end up with the total stiffness as a weighted average of all the stiffnesses. For example, we said that for the A matrix, Aij is summation of Qij times the Zk minus Zk minus 1 term, which means for a certain stiffness in a certain direction, let's say the 1, 1 direction, you take the stiffness of each ply in that direction and multiplied by this, this now becomes a weighting factor. It so happens if all the plies have the same thickness, this term would be exactly the same, but not all the plies will have the same thickness in a general design if you use different materials. So there's a weighting factor, and this then makes it some kind of a weighted expression. So in stiffness, everything contributes and somehow will be put together. In strength, the weakest link is what starts everything, and it has nothing to do with how strong you are in other locations. And the weakest link in general, if you think in terms of the constituents, which are the fiber and the matrix, is the matrix itself, unless you are using metal matrices, which are extremely expensive and not commonly used. But let's say we are dealing with composite materials where the matrix is typical resin of today, which would be extremely weak compared to the fiber. So that's what will fail first. And as you can imagine, if it's not a very strange stacking sequence, then that failure does not mean that the fibers, all the fibers around that failure will fail. So load gets transferred from the matrix that broke to adjacent fibers through matrix that's still intact, or even through the broken matrix, and you can still carry load. And in fact, you can move load away from the plies whose matrix has failed to other plies and then behave as if you had absolutely no knowledge of that local failure. Going back to the picture we saw before, these are zero plies, so the fibers are running as from left to right in the middle, and these are minus 45 plies, and the little dots, essentially those white speckles spots, are just the fibers coming towards us at an angle of 45 degrees. So this is a crack at the top left here into the matrix, which basically occurs in between fibers. Similarly, this is a crack here. Now, that happens very early. If you imagine a tensile load being applied, it happens very early because the matrix is weak. And even if I break this here, all that means is somehow I take the load that was into this bottom right portion, transfer it through the very stiff fibers here, and bring it back into the structure or the ply behind this crack. And you can do the same thing here, unless cases where you have delaminations, which means you cannot take load from here to here now because they have separated. So the mechanisms are there, and I'm trying to indicate that there's multiple mechanisms, and what happens first is not necessarily what relates even to what happens last. Or if it does, it's a fairly complex process going from one failure mode to the next. When the fibers break, of course, it's much more interesting, and you can see here that we have a whole bunch, the thickness of the laminate is in this direction, up or down, and all the plies have completely failed, and there's also some delaminations. So that's the ultimate goal, predict what's on the right, but we will start with trying to predict what's on the left, and we'll sort of stop there because we will simply raise our hands up and admit complete defeat. So let's get into the failure modes of a ply in 15 minutes. That way we'll maintain the momentum. This is close enough to 15 minutes, minus half a minute. One correction, when I was writing the inverse of the A matrix, I had the A22 here and A22 there. This A22 is correct. This one was wrong. It should say A11. That's an oversight, thanks to the gentleman that pointed that out. Now, before we continue, we'll actually play, as I was saying, spies or detectives, composites detectives. I mean, imagine your business, your job is being a composites detective. But it can be interesting. Where's my chart? There it is. So back in December, Airbus did the ultimate load test of their wing. And watch out the picture. I mean, can you give me any information, man? Or are you, whoops, hang on. Are you just, if I even enlarge it, right? So what do we see? We see, if we use our imagination, that there's a fuselage here. These are the cockpit windows, so it's coming at us. And this is actually the one wing and the other wing. And this is the so-called wiffle tree, which is the scaffolding that applies all the loads. And talk about not giving any information. It's a picture which could be like my son playing with his Meccano thing, and with the proper coloring, it could easily have been that. But the fact remains that they actually did it. And let's read a little bit because it's interesting. The company states it has applied up to 1.5 times higher than those the aircraft or the loads. Successfully performed the ultimate load test. The company states it has applied loads up to 1.5 times higher than those the aircraft would ever encounter in its entire in-service life. This is public relations at its best. I mean, everybody knows this is the ultimate load. It's a requirement. You don't just do it because you are conservative. You are told by law you have to apply 1.5. But if you write it this way, it's a wonderful way of bringing in a sense of security, because people say, okay, they actually multiply by 1.5. Now, they forget that if you get in an elevator, the safety factors there are 8. They actually multiply by 8, but the weight is not an issue. But, and if they thought about that there are some people that are afraid getting into elevators, if you told them it's a safety factor of 8 and you're still afraid, what would you do if the safety factor is 1.5? I think that will increase the number of people that are afraid in getting in airplanes by a lot, including my wife. I haven't told her that. Wingtip deflection exceeds 5 meters. Okay, that sounds phenomenal, but if I tell you now it's 32 meters per wing, so it's 64 approximately total. So I have, where's my chalk? Basically 5 divided by 32 is the tangent of the angle, right? So if this is my wing and it's cantilevered here, yes, I know it's actually bends, but, well, let's do it bending so the purists among you don't complain. So the wing does this, and this is 5 meters, and this is 30, what did I say, 32. So if it were straight, which would mean it would even be a bigger angle, you know, this angle here would be the tangent is 5 divided by 32, which is 0.15. No, I don't just do tangents in the back of my mind. I have done it, and hopefully I remember correctly when I did it. This one, which translates to approximately 8 to 9 degrees. So you have a beam which it's fairly sizable and only has a angle here that's, or this angle here is 8 to 9 degrees. Why am I saying all this? So is this a linear theory or a non-linear theory? Is this large deflections or not? I think it isn't. The point is, knowing your beam theory now and knowing this size and this and that angle, you can take non-linear beam theory, which involves elliptic integrals if you're so inclined, or just the standard forget-me-not equations that we've done in the good old days, assuming some kind of a constant lift distribution. But calculate the EI, or an average EI. You can calculate the average EI for this. And knowing the average EI, you can then make a statement about how thick is the skin, because you have to reproduce that EI given a certain geometry. And the core depth is approximately known. If you look into Wikipedia, you can find that. So you can actually do that game, and you say, okay, you reach certain conclusions. Airbus, we'll continue on this in a bit. Airbus explains it already passed the last of the ultimate load tests for the fuselage. So that's great. Basically, they are done with the static testing. And of course, here's the story about they analyze the huge volume of data is analyzed and correlated to the structural computer models. You know, this is just I have a finite element model and I take all my strain gauge data or other type of data and I have to show that they match. If they don't, I have a problem. Remember this. Company states it has applied loads up to 1.5 times higher than those the aircraft would ever encounter in its entire service life. Now let's see how the 787 announcement was when they first came out with the same story. First of all, look at the picture. Do you see any similarities? It's a completely different company, each at its other's throats. They would kill for a useful picture, but they both know how to give you a useless picture. Here's the exact same thing. The 787 cockpit, the wing, bending like crazy, and all the scaffolding so you cannot see anything. And I mean, I don't blame them. I would probably do the same thing, but it just makes it harder for us to try to deduce a few things. So now remember what we were reading. This was back in March 28th of a couple of years ago. Today completed the ultimate load wing upbending test. At least here they give us a little more information. It's upbending. I mean, you can tell by looking at it, but at least they say it. On the 787 Dreamliner, during the testing, loads were applied to the airframe to replicate 150% of the most extreme forces the airplane is ever expected to experience while in service. Makes you suspect that the PR person, the public relations person, is the same. They just changed companies, and they said, this is what we'll give to those guys. It's the exact same framework. Give them a feeling of this being a very good piece of work, which it is, a very safe piece of work, which it is. But don't tell them, okay, this is legal, by law they have to satisfy this. It's just because it sounds so good to know that there's a safety factor of 1.5. The wings were flexed upward by approximately 7.6 meters. Now this is interesting because the wing is shorter. Remember, the 787 is slightly smaller. So I would have 7 divided by 30, which would make the angle bigger. And you can sort of tell by looking at the picture now that this is really bending up. And of course, this may not be at ultimate load, may be more than ultimate load. They never tell us. But the point is the angle would be bigger, so I would expect the 787 to be more flexible. So the EI that one would back calculate would be smaller. And that would make some interesting thinking in terms of, okay, flexible wings have certain aerodynamic properties that are desirable, but also their dynamic properties might not be. So it would be interesting to carry this further, and every once in a while we'll be doing some of this, not necessarily on the same topic, because it can take 3 months, and then we would be off by a factor of 2 in the end if we don't have all the information. But that is where we are. As of December, the 787 has passed the full-scale tests, and if I can find my correct file. Yes.